In this lecture, we will see heap. Before seeing heap, let's revise few topics. Number one is binary tree. A binary tree is a tree in which every node has 0, 1 or 2 children. If we take an example, this is a binary tree. This node has 2 children, this node has 0 children and this has 1 child. There are different forms of binary tree. There is a strict binary tree. In a strict binary tree, every node has either 0 or 2 children. So if we take an example, this is an example of a strict binary tree. Every node has either 0 or 2 children. Then there is another form of binary tree which is known as perfect binary tree. Perfect binary tree is a tree in which all levels are completely filled. So if we take an example, this is an example of perfect binary tree. Every level is completely filled. One more thing we need to see is that in a perfect binary tree, n by 2, n is the total number of nodes, then n by 2 and the seal of that number of nodes will be present as a leaf node, and n by 2 and floor of that will be as the internal node. For example, there are total 7 nodes here. So if we do 7 by 2 and the seal of that will be 3.5 seal and it will be 4. 4 nodes are present as leaf node, and if we do this 7 by 2 floor is 3.5 floor is equals to 3, and 3 nodes are present as internal node. Next we have complete binary tree. A complete binary tree is a tree in which all levels are completely filled except probably the last level, and the nodes in the last level are as left as possible. So if we take an example of this, a single node, this is a complete binary tree. If we take the left child, this is also a complete binary tree. This is also a complete binary tree. This is not a complete binary tree. Why? All levels are completely filled except probably the last level. The last level is not completely filled, but then all the nodes in the last level should be as left as possible, but there are 2 positions empty to the left of this node. So this is not a complete binary tree. But if we fill this like this, then this is a complete binary tree. Now, if I give some numbers here 1, 2, 3, 4, 5, 6, and I fill this in level wise in an array. So I will be able to represent this tree in form of array. So the numbers in the array will be 1, 2, 3, 4, 5, 6. Level wise, left to right, then top to bottom. Here, what we have in tree, the parent-child relationship, that relationship should be here. So if I have a key at index 1, then we should have some formula by which I can find its left and right child. If a node is at index I, then its left child will be at index 2 into I plus 1, and the right child will be at the index 2 into I plus 2. Let's see. The left child of 2 is 4 and the right child is 5. 2 is at index 1. So left child should be at index 2 into 1 plus 1 should be 3. So at index 3, there is 4, which is the left child of 2. And the right child of 2 should be at index 2 into 1 plus 2, which is 4. So at 4, there is 5, which is the right child of 2. So the formulas are working. You can try this on few other indices as well. Now if we have child at index I, then the parent will be at the index I minus 1 by 2 and the floor of this. So if I want to find the parent of 6, 6 is at index 5. So 5 minus 1 by 2 floor is 4 by 2, floor is 2. So the parent of 6 is at index 2, which is correct because parent of 6 is 3 and it is at index 2. If I want to find the parent of 5, it should be 4 minus 1 by 2 because 5 is at index 4. So it will be 3 by 2, 1.5, floor of that will be 1. So the parent of 5 should be at index 1, which is 2, and it is correct that the parent of 5 is 2. So these formulas are working, so we can use this formula. So why we revise this concept of binary tree? Because our heaps are complete binary tree. We'll be talking about heaps in more specific way. We will be talking about binary heaps, and in the binary heap also we will be talking about min heap and max heap. So we have property of in min heap that if we have a parent and there is 2 child C1 and C2, then in min heap P will be less than C1 and P will be less than C2. So P will be less than both C1 and C2. And in the max heap, if we have parent and left child as C1 and right child as C2, then P should be greater than C1 and P should be greater than C2. These conditions are true at every node in min heap and max heap. And since heaps are complete binary tree, they are stored as array. So we can convert any array to heap, whether it is min heap or max heap, in order n. So what do we need to do? We need to, suppose we are given with an array 3, 9, 4, 5, 1, 2. If we represent this in the form of tree, it will be 3, 9, 4, 5, 1 and 2. So neither it is min heap nor it is max heap. So let's convert this to a max heap. What happens is that we will start from n by 2 index. So we will leave the leaf node right now. We will start from here. So we'll check, suppose we are creating a max heap. We will check whether this 4 is satisfying the property of max heap. And what is the property of max heap? That 4 should be greater than both of its child. So 4 is satisfying the property of max heap. So we will not do anything here. Then we will do I minus minus. So we'll go to 9. We'll go to 9. We will check whether 9 is satisfying the property of max heap. Yes, it is satisfying the property of max heap. We'll not do anything and we'll do I minus minus. So we'll reach 3. We see, is 3 following the property of max heap? No, 3 is not following the property of max heap. So we'll see what is the maximum among the child. 9 is the maximum, so we'll swap. So 3 will be swapped with 9. Then we recursively check on this node as well whether this is following the property of max heap. No. So what happens, we will see which is maximum. 5 is maximum, so 5 will come here and 3 will come. And now this is a max heap. 9 is greater than 5 and 4, 5 is greater than 3 and 1, 4 is greater than 2. And in the array also it will be changed to 9, 5, 4, 3, 1, 2. Let's code this and let's see how this will work. So we will have one function build heap which will not return anything. It will take an array and its size. What it will do is it will call a function heapify on every known leaf node. So it is starting from n by 2 and it is going till 0. We know that n by 2 nodes will be there in the leaf node approximately, right? In complete binary tree, there will be approximately n by 2 nodes in the leaf node. So we will leave those nodes and we will just go from n by 2 to 0, right? Even if n by 2, there may be a case when n by 2 is a leaf node, then also it will not affect the output, right? If even 1 or 2 leaf nodes are there. Now heapify, how it will work? Let's see. It will not return anything. It will take an array. It will take its size and one index on which we will have to call the heapify. So when we are calling the heapify function, we are checking each node with its child. So what will happen? We'll calculate the child for ith index. The left child will be 2 into I plus 1 and the right child will be 2 into I plus 2. Now since we are making a max heap, let's suppose that the maximum among all means I, C1 and C2 is I only for now. Then we will check if C1 is less than n. So it means if C1 is in the range of the array and the value at C1 is greater than the value at maximum, then we will say that maximum is equals to C1. And we will do the same thing for C2 as well, and there is no else if, there is if and if. Why if and if? It may happen that C2 is greater than C1 as well. So this both conditions should be checked. So now we will do maximum equal to C2. And if maximum is not equals to I, it means that this I was not following the property of max heap. So maximum will not be equal to I. So what we will do, we will just swap ARR of I and ARR of maximum. So we'll swap it with the child whichever is maximum, and we will call this recursively on the child as well, because now my current node has gone to the index, maximum index. So what will happen? Now it has to check recursively for the child at maximum index as well, whether it is following the property, similarly to something which we did here. So first we compare 3 with 9 and 4, we replace 3 with 9, and then we recursively check 3 with 5 and 1 as well. This will create any array into heap. Okay, so this function takes order, and we will see in some other lecture how it is taking order and time complexity. Now suppose what happens is there are two other functions here. One is extract max in max heap when we need to extract the maximum, and there is extract min in min heap as well. The functionality of both are same, and another function is insert. Let's see how that works. So we have this max heap and I'm calling extract max. The maximum will be at the root. if you directly remove this maximum, then what will happen? 5 and 4, which is larger, 5. So 5 should come here. And 5 will be removed from here. Then 3 and 1, which is larger, 3. 3 should come here. And 3 will be removed from here. But then, now this is not a complete binary tree. And we know that our max heap is a complete binary tree. So this is not a right method. There is one node. Even if I remove that node, then also it will be a complete binary tree, and that node is 2. So what we will do when we are doing extract max, we will just swap this 9 with this node. So this is 2, this is 9. Now what we will do n minus minus. So this will be there. It means this is in the array, but it is not visible to the program. Program does not know that this 9 is there in the heap, because we reduce the size by which it was checking. So earlier the size was n equals to 6, now n equals to 5. So we will have array from 0 to 4. This 9 is at index 5, but we have index from 0 to 4 only, so program will be able to see only this. So first we will swap the first and the last element, 0th and the last element. Then what we will do? We'll call heapify here on the 0th element. So 2, 5, 4. It is not following the property of max heap. So which is larger? 5 is larger. So we'll just swap 2 and 5. 2, 3, 1. Not following the property of max heap. 3 is larger. So we'll replace 2 by 3. Now our heap will become 5, 3, 4, 2, 1. And this 9, which is not visible. If it is not visible, then we will not consider it in the property of heap as well, right? Why I am not deleting this, I will let you know when we will study heap sort. But right now, this is how we do extract max, and then we can return ARR of n. N is 5, so ARR of 5. This is at index 5, so we'll just return the value of this. And this is how extract max work. Then there is a method of inserting a new node. Suppose I want to insert 10 in this heap. So what will happen? I cannot just randomly insert 10, or I cannot just insert 10 at the top and then call heapify or 9. We cannot replace 9 with 2 or something like that. So what we will do? We will just insert 10 at the last position. We'll just put 10 at the last position. Then what we will do? In heapify, we were checking with the child. This function is called percolate up. Heapify is also called percolate down. So we'll call percolate up. So 10 will be compared with its parent. So 10 is greater than the parent. So 10 and its parent will be swapped. Then 10 will be compared to the parent. 10 is greater than the parent. Then 10 and that parent will be swapped. So our heap will become 10, 5, 9, 3, 1, 2, 4. And this is our max heap. So this is how we insert the element in the already built up heap. Just try to write the code of build heap, insert and extract max for max heap. Next we will see heap sort. Thank you.